So, a little bit about myself. I'm Thomas Orth. I'm a senior AI engineer at Lockheed Martin. One of my favorite things about my job is that I'm able to use Gen AI to apply across different industries and applications at Lockheed to enable real change in our business practices. I'm staying ahead of the tech curve and learning about new trends through pursuit of a master's degree at Georgia Tech, which is really helping me learn a lot more about AI and the generative AI space. So, the main problem I'm trying to tackle is one that a lot of us have encountered. As developers, we work on projects that have large code bases ranging from thousands to hundreds of thousands of lines of code. The issue is that the architecture and execution of these programs are not always documented effectively. Whether you're a new developer or an architect, it could be a daunting task to find up-to-date documentation that accurately reflects your project. And in order to update those documentation, it takes a lot of time and effort in order to upkeep those documents. While an LLM alone isn't the answer to the problem, an LLM can help vastly in maintaining the documentation of these large-scale code bases. So you might be asking, why can't you use an LLM all on its own? Well, there's a few key reasons. The first being LLMs have a limited context length. In this, we mean that the context length refers to the amount of text tokens that the LLM can ingest as we're talking about code. A token is just the representation that an LLM sees when it looks like characters and words. Some LLMs, like Flash 3, have a really limited context length of 64,000 tokens. Other LLMs, like Llama 3.3, have a really large context window at 128K, but they all have the same thing in common. They all have their limits. More so, not only do they have limits, an LLM isn't going to know right off the bat what's the most important part of your code. Same way if you hire a new, junior developer to your team, they're not going to know what the core microservice of your project is. They're going to need to be told what that is. Additionally, an LLM can tend to generalize its output and not be very informative. I had that happen on this project where I first was trying to generate documentation, and the output was really generalized and missed a lot of the information I was looking for regarding a security architecture. In order to mitigate this, a tool is needed to ground the LLM in fact and semantic reasoning to allow for key documentation to be generated. I'll direct you to the image on this slide, where we're going to start at the top right. This image as a whole represents a knowledge graph, which is the tool me and my team decided to focus on to ground our LLM. You notice on the top right, we have nodes of blue and green. In this context, the color doesn't matter too much, but they can signify different nodes within your graph. Each of these nodes are connected via edges, and those edges connect to each other and represent relationships. These relationships give semantic meaning to the different nodes within your graph. By using a knowledge graph to solve this problem, we can capture meaningful relationships within code projects and relate different nodes, which are code files within your project, to have the relationships that an LLM needs in order to document your code base. The cool part is, with a knowledge graph, it's a repeatable data structure across different languages. So you're not creating a bespoke solution for something like Java and needing a different bespoke solution for Python. It's repeatable and scalable. So a lot of you who have worked in the code parsing space might have run into the same challenges I've run into, which is that a lot of solutions are rather bespoke and don't scale very well. There's packages that can parse out syntax trees for Python, but not for C++, or there's a library that works really well for Java, but doesn't really work well for C++. You need a solution that scales well and works for multiple languages. I hit a wall and I was trying to find the package that would help until I came across TreeSitter. It's a really neat open source package that supports a multitude of different languages that allows for the parsing of code to create abstract syntax trees for a multitude of languages. Additionally, it provides an interface that allows for easy tracking of nodes so I can find the key pieces of information I need, such as import statements, function names, and class definitions. Using TreeSitter, I'm able to get a lot of semantic meaning out of the code so that I can build my knowledge graph in order to ground my LLM. So now that we've talked a little bit about TreeSitter, I'm going to talk a bit about the relationships within the knowledge graph, specifically two that capture a lot of semantic meaning within the code. The first one we're going to talk about is import statements. The second will be class interactions. As developers, when we develop code projects, we have a multitude of different files, and those files typically are linked via import statements. If you've ever worked on a Python project, you've definitely done, a from package import class statement in your time. Well, we as developers know that relationship. An LLM isn't going to know that themselves, and more importantly, won't be able to automatically link code files. By using Tree Sitter, we're able to parse out import statements and use different resolution strategies to validate internal project code versus third-party dependencies, so that we're ensuring that our knowledge graph represents the import statements relevant to our code base instead of third-party code that we do not maintain. Using directed edges, we can also note the flow of the import so that this way we capture all the semantic meaning within that information. Now, you might be asking yourselves, aren't we going to get all the information we need from import statements? And the answer is actually no. Some languages actually have other information with them that isn't captured by import statements. An example of this is the Java language. Classes of the same package can be leveraged in different files for Java, but without an explicit import. When I was originally working on this project, we made the assumption that import statements was the only relationship we needed. But when we were generating knowledge graphs, we noticed that key information was being missed. And when we inspected the erroneous issues, we found that it was this exact thing where Java wasn't having explicit imports. So using Tree Sitter, we actually were able to locate class interactions at the line level and figure out exactly how to link files together. And once we were able to do that, any information we couldn't get through our import relationship, we could then get through our class interaction relationship. Once we've extracted our relationships, we're able to actually look at the code abstract syntax trees. I'll direct you to the graphic shown here, which just shows an example of a syntax tree as you parse out your code. By parsing out an abstract syntax tree, we can actually look at the key artifacts within a code file in order to determine what's the most important code to provide the LLM. In this basic example here, we can start at the statement sequence and actually drill down into while loops, the comparisons, and the specific variables. For this project, we look specifically at the class level and function definition level to provide key traceability artifacts to the LLM to ground it using our knowledge graph. Now, this slide here seems like it has a lot of information and a lot of text, but it's rather important for us to go through. First, I'm going to explain why we need to actually use graph theory to identify important nodes. Second, I'm going to explain the strategy we have for identifying those important nodes. And finally, I'm then going to go over the impact that has on the LLM output. So if you recall, when I was detailing the deficiencies of an LLM is not going to know what's your most important code on your code base. In order to know that, you're going to have to tell it. With our knowledge graph, we can apply graph theory in order to use different attributes and parameters of that graph to identify what actually is the most important part. Our current strategy is that we look at nodes with the highest number of out edges. Now, for us, an out edge is a directed edge from a starting node to a destination node that captures the import and class interaction relationship. We identify that a node with the highest number of out edges signifies that it imports most of the logic within the code base, potentially signaling that it's the most important part as it's a key entry port in order to run the code base, which allows the LLM then to traverse that code base to find the important parts that it needs for a diagram. By grounding the LLM in looking at the most important nodes, we're able to guide the LLM to look at the correct spot rather than it trying to make overgeneralized assumptions about our code. This has worked really well as we're able to really point the LLM at what we needed to look at for the code base. So what have we covered so far? We've talked about how we load our code base into a knowledge graph, how we extract relationships with Tree Sitter for import statements and class interactions, how once we have those relationships, we can actually look at the abstract syntax tree for class information and function level definitions, and then finally, how to actually mark a node that's most important within that graph for the LLM to look at. Once we've done all that, we can start clustering around different diagram topics so that we can further subset our graph so that we can choose what fits into our context and has the most important information for the diagram we're creating. On the next slide, I'm going to actually talk a little bit about the diagrams that we'll be generating and the diagramming language that was used. So all the diagrams created in our tool uses the Unified Modeling Language, or UML. It's a staple amongst the software engineering community, and it's really a powerful tool to capture key information about architecture within your code bases. For this presentation, we're focusing on 3 diagrams the tool can make. The first is the activity diagram. This is a high-level diagram that can model the data as it flows through a process. Let's take, for example, a simple e-commerce application where a user has gone in and bought a t-shirt. An activity diagram, in this instance, will walk through the high-level activities going through the application so that from purchase to transaction, we can see the high level movement within the service so that the application can complete that transaction. A sequence diagram is slightly similar, that it captures the same information, but at a granular level. That granular level captures actual classes and shows their interactions via messages over a timeline window and their completion to provide results to the user. The final diagram is the class diagram. This shows the different class structures and components, including methods, attributes, and some relationships. Going back to the e-commerce application, this will actually show the underlying classes used for the application, such as a manager class to actually manage shopping transactions, a t-shirt class maybe to map some attributes for, and a shopping cart class that will show the inventory that a shopper has added during their shopping trip. On the next slides, we're going to walk through diagrams that the tool we've shown here through LLMs and knowledge graphs have generated in order to illustrate the functionality of the tool that I've been working on. I've chosen this open source library called Spring JDBC, where JDBC stands for Java Database Connection. I chose this library because it's a rather popular Java library for database operations. I also chose this because it's a rather large repository. When you count up the number of tokens within the different code files, it's more than 128,000, which is the max for modern day LLMs for high performance in open source software. I chose this because of the fact that this really illustrates the functionality of the tool, that we need to choose the most important parts of the code base in order to create diagrams, not just because the LLM won't be able to figure it out itself, but because most times it's physically impossible to actually ingest the whole code base into the LLM at one time. So first, this is the activity diagram of that Spring JDBC. It's focused primarily on the creation and execution of SQL statements. As you can see here, the software and the LLM has produced a flow graph where we have our starting point here, creating our connection, and we go through the preparation of our statement. We have some conditionals where we determine whether or not what path we have to take within our activity. Going through the full graph here in the activity diagram, all the way down to the bottom where we've got our exit condition as the connection's been closed after the statement's been executed and results have been retrieved. This is, again, a high-level diagram that executes or shows the flow of the activity within the application. Now, we're going to look at a sequence diagram. This shows the same kind of information that our LLM and knowledge graph tool was able to extract from the JDBC repo, but at a different viewpoint. Like I mentioned, this is a little bit more of a granular level, as now we're looking at the specific classes within this project and how they interact with the messages via a timeline. As you can see, a user will actually call and execute against the operations class, look to get a keys from its key holder, and we'll see the return of those messages back to the relevant classes. And as it goes all the way through, we actually can see the results being sent back to the user. This is a slightly different view, like I said, from the activity diagram. And much like the activity diagram, the sequence diagram is not one that you can easily create through static analysis tools. The activity diagram and sequence diagram take a non-trivial amount of time for an engineer and architect to develop. So by using LLMs and knowledge graphs, this tool allows for automation of that task to free up engineers to focus on other tasks that need their attention. The final diagram we're going to walk through is the class diagram that my tool has generated. If you notice here, we have those same three classes we saw in the sequence diagram, but the LLM and knowledge graph was able to capture the different methods associated with each class so that we can see what each class is possible of doing within the code base. You'll also notice that we're able to capture the object-oriented relationship between keyholder and JDBC operations and SQL row statement and JDB operations. This is another more granular view. While we're not looking at the activity within an application, we are able to get a viewpoint into what is attached to each of these classes for what's the most important classes within this code base. And while that's the end of the technical content about how using the LLM and knowledge graph was able to produce really grounded documents and optimize the documentation process to free up engineers, I want to take time to acknowledge the technical team that worked on this. The engineers and leads who helped work on this project really helped on the execution and really delivered some key milestones in recent months. And without them, it wouldn't have been possible. I'm just one part of the team, and I want to make sure that they get their due praise and acknowledgement. So I'm just gonna, leave the slide up here for a few seconds so that the team is acknowledged. And with that, that is the end of my presentation. Thank you all for coming, and I'll be happy to answer any questions.